Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, we'll continue the topic of two-factor ANOVA, describing how to look at the individual model components and also the actual full model testing. So in the last lecture, we ended by talking about the calculation of the full model R squared and how it is really calculated in a very similar way as the calculation for the R squared for the full model in multiple regression, and how the interpretation is exactly the same. So it's a simple extension of this to calculate the component R squared effect sizes. And the component R squared effect sizes are simply an R squared for each predictor, and we're going to have a really similar interpretation as the full model R squared. And the way that we calculate each component R squared is by taking the sum of squares for each individual predictor and dividing it by the total sum of squares. So we can see here the calculations for the R squared for gender and the R squared for video game condition. And the R squared for gender is calculated out to be 0.08, and the R squared for video game condition is at 0.39. So the way that we would interpret these is that we would say that predictor 1, or gender, uniquely explains 8% of the variability in aggression, and then we would say video game condition uniquely explains 39% of the variability in aggression. And so these component R squared effect sizes are really useful in that they give us some metric to see how well each of the predictors is predicting the outcome. So just by looking at these, we can see that we think probably that video game condition is explaining a lot more variability in aggression. And so video game is really our strong predictor that would be driving that full model, if you will. And the only difference in the interpretation of the component R squared values versus the overall R squared is that we're saying that each predictor is uniquely explaining this amount of variability in the outcome. And so here is where we would find the information to calculate those component R squared values. As you can see, they're not printed out in these tests of between subjects effects. We would have to calculate them in this way by taking each predictor sum of squares and dividing it by that total. And the component R squared effect size, it's also known as a partial R squared. And so the component R squared effect size, because it's for each individual predictor, the cutoffs are smaller than the full model R squared because each predictor doesn't have to be explaining quite as much variation in the outcome to be considered, a meaningful effect, a large effect, really. So the cutoffs for the component R squared are that negligible is less than 0.01. Or 1%, small is 1% to 6%, moderate is 6 to 14%, and large is 14 to 100%. So anything greater than 0.14 is considered a large effect size. Okay, and then we've talked about the mean squares, which we know are a simple extension of the sums of squares. We are just dividing the sums of squares by their degrees of freedom. And now we have the degrees of freedom that are calculated in much the same way as the degrees of freedom from the one-way ANOVA, where we have each mean square is equal to the sum of squared divided by its degrees of freedom. And the degrees of freedom for the first predictor is going to be that number of groups minus 1. And for the second predictor is that number of groups on that predictor minus 1. So the degrees of freedom for gender, the degrees of freedom is 1 because there are only 2 groups. So 2 minus 1 is 1. The degrees of freedom for video game condition are going to be 3 minus 1, which is equal to 2. And then we have the error degrees of freedom, which is going to be n minus 1 minus the degrees of freedom for the model. And the degrees of freedom for the model is going to be 3 because that's the sum of the degrees of freedom from the 2 predictors. So because we have 30 participants, minus 1 minus 3 is going to be 26 degrees of freedom for the mean square error. And here's where we find that information on the mean squares in the SPSS output, and you are familiar with this by now. So let's talk about the model testing steps a little bit. The first place we're going to start for model testing with the two-way ANOVA is to test the full model. And if the full model is not significant, that is, if the overall F-test is not significant, then we stop testing. And we don't go on and assess the main effects because the full model wasn't significant. That means that we haven't really explained a lot of variation in the outcome with our set of predictors. The predictors are not statistically significantly predicting the outcome as a whole. So to test the full model, we look at the full model F, and that's going to evaluate whether the effect of both predictors, or the cumulative effect of the predictors, is zero in the population. And so the null hypothesis for this full model is that all observations belong to the same population. That is to say that we would be testing whether or not all of the group means are equal. All of the means are the same. And to get this F, we take the mean square for the model divided by the mean square error. And this evaluates, again, whether that set of predictors cumulatively explain the variation in the outcome. And this should look familiar to you because this is exactly how we calculate the F-test for the full model in multiple regression. So we take the mean square for the model and divide it by the mean square error, and that gives us the F statistic. And if the F statistic is significant, this is implying to us that at least one predictor is influencing the outcome, if not both. And here's where we find that information for the F-test in the SPSS output. This concludes the fourth lecture on two-factor ANOVA, and in the next lecture, I'll describe assessing significance for the main effects.